Hey guys, this is Terence. Welcome to the second episode of RhinoPython and GhPython Playground. And in today's video, I'm going to introduce how to create this set of pattern, this matrix walls. To create this pattern, we will still use some techniques we already talked about in the first video, like Python dictionary, like point matrix, and some randomness functions. Today, we will also introduce some new functions like subdivide surface, like rebuild surface to make this pattern looks dynamic but still under our control. So let's get started. At the beginning, I want to quickly go over the whole process of generating this pattern. We can start from generating a point matrix. And in this pattern, we only need 2 layers of points. Based on these points, we can generate 2 layers of polylines or squares, like this. Now we have 2 layers of squares. The basic idea is we keep the back layer unchanged and modify the first layer of squares, make it smaller, subdivide it or something, just like this. Now we have many small windows. The last step is to loft these 2 layers of polylines and make it solid. And let's run it. This is the pattern we want. Let's do it step by step. At the beginning, we can write a function to generate the point matrix. We need to import the RhinoScript syntax SRS. Then we define a function which is called generate matrix, which takes 3 parameters. They are the number of points along the x-axis, I call it x number, and the number of points along the y-axis, y number, and the number of points along the z-axis as well. Inside this function, we need to first declare an empty dictionary called pointDict to store all the points. Now we loop over all 3 axes. For z in range, z number. For y in range, y number, and for x in range, x number. Inside these nested loops, we can add points into the dictionary by the xyz index and xyz coordinates. We can say pointDict with the key x, y, z equals to the coordinate x, y, and z. Now I want to make the spacing between points much larger. I can multiply the x coordinate by 10, z value by 10, and y value by just 5. Y value could be smaller, but x, z value could be equal because we want to generate some squares on xz plane. After storing all the points into the point dictionary, we can write some code to show this point in our Rhino space. We can loop over all the we can just add points. rs.addPoints and convert the dictionary into a flattened list. ptdix.values. Now we have our basic function, but we haven't run it in the space. Outside this function, we first define x value, x number of points as I can make it 5. Y value make it 2. We just need 2 layers of points, and z value as 5 as well. Then we call this function generate matrix with x, y, and z. Let's try it out. Now we have our points. And then I want to add some tags on these points to make the structure much more straightforward. I can say here inside our function, we can add another parameter called show tag, which equals to false by default inside this function. Create conditional statement. If show tag, then we loop over all the keys inside the point dictionary. For key in point dict, we can add text dot with the text of key, and the second input should be point or coordinate of that point, which is point dict at the location of key. Now let's try it to see. Oh, sorry. Here should be true. Now we can see these tags here, and the tags are indexed instead of the coordinates. We can see the structure of the dictionary. This is 000, this 100, and this 110. This is a much more straightforward way to show these points, to show the structure inside the point dictionary. Then we can take advantage of this structure to draw many polylines. Now this is our first function. Okay, I want to add another layer of control on our first function. I want to say show points. We want to have the control on showing the points or not. By default, show point is false. And here I can say if show point, just add points. At the end of this function, we return the point dictionary. Here at point dictionary equals to the generate point matrix. Make this true. Run it again. Now we finished our first function. The next step is to draw polylines, to draw squares based on the point matrix we just generated. Now, in order to make things more clear, I want to remove these repeated parts and just keep 8 points. This is our basic module. The polyline we want to create are these two. This is the first layer. I call it the back layer, and I want to start from here. This is the front layer. Instead of putting these 2 layers of curve in one list, I prefer to separate them because I want to keep the back layer here unchanged, but modify the front layer here. So let's achieve this by codings. We can define another function here called draw polyline, which takes 2 parameters. The first one is point dictionary, and the second one, as we mentioned, we want to separate these 2 layers. So the second input could be the layer identifier. I say it as y equals 1 by default. This means I want to generate the back layer of the square because this layer's y index is 1. If I set 0 here, this means I want to create this layer of squares. Inside this function, I first declare an empty list called polylines equals to an empty list. Then I want to calculate the max x index and max z index in the dictionary. For sure, I can directly take the value here, but as our code is growing bulkily, many errors might take place in many different functions. I just want my code always keep precise. So I want to recalculate the x max value and the z max value inside this function. I can say x max equals to max. It's a function. with the list comprehension key 0 for key in point dictionary. This line of code means we loop over all the keys inside this dictionary, then pick the first item of the key, which is X index, put all these X indexes into the list, then calculate the max one. This is what this line of code means. Hope this explanation makes sense. We do the same thing on the Zmax. Key 2, because the Z index locates in the third position of the tuple. This is 0, this index is 0, 1, and 2, so the index of Z value is 2. For key in point dictionary. Now we have our Zmax and Xmax value. We just loop over these two directions, X direction and Z direction. Range Zmax, and for X in range Xmax. Now we can pick this point manually. This is a hard coding part. Point A as our start point is X, Y, and Z. We already have our Y here, and let's repeat this process 4 times. Point B equals to the second point. We want to draw this polyline counterclockwise. So this is our start point. This is our second point. Here is X plus 1 and Z. The point C is X plus 1, Z plus 1, and the last point, point D, is X, Y, and Z plus 1. Now we have all the points we want. To use to generate the polyline. We can call this function as append rs.addPolyline, which takes just one parameter. It's a list of points used to generate the curve, generate the polyline. We can just put all our points into this list by sequence. And point D. And at last, don't forget to put the first point at the end of list to close the curve. Then we can just append this polyline into our polylines list. Append. And finally, return these polylines. Now we can test this function to see if it works. We can say back polys equals to draw poly point dictionary. Remove this, run the code. It works. And we also try, does it works in the first layer, in the front layer. We can say front polys equals to draw poly point dictionary with the layer index 0. We delete this and run the code again. This is what we want. Now we can try to increase the X number and the Z number to see if it's still working in a larger context. Okay, now this is what we want for the second step. The third step is by far the most interesting part in this playground, I think, because we want to find a way to transform this square, to make it smaller, to make it move around, to create a dynamic looking, but at the same time we still want to have some controls on the position and the size of the small squares. So my solution is, let me draw a square at first. This is our basic cell, a square. I want to divide it into a 3x3 grid. Then we have options on these nice small squares. And as well, this grid provide us with many possibilities, like we can combine two squares into a large rectangular in this direction and in this direction. And also we can combine these 4 small squares into a large 2x2 square like this. Now let's think about how many options do we have in this 3x3 square. We can have a 1x1 basic cell here. We can have a 1x2 rectangular here, 1x2. We can have a 2x1 rectangular here, this one, this two, and finally we can have a 2x2 large square here, 2x2. Now we have 9 options on this shape. We have 6 options on this shape. You can see 1, 2, 3, 4, 5, and 6. And in this vertical direction, it's 6 as well. And at last, we will have 4 options, 2, 3, 4. 4 options on this large square. So let's sum it up. We will have 25 possibilities that can generate from this 3x3 grid. I think this is already a lot of possibilities, and the result is for sure under our control. Now let's go back to our code. We can define another function here called Subdivide, which takes only one parameter. It's a single polyline. I don't want to put the whole polyline list into here. I just want to keep the function very, very concise. We can loop over all the polylines outside this function, but inside here we just deal with a single polyline. In terms of dividing this square into a 3x3 grid, my solution is I first make it a surface, then I rebuild this surface into a 4x4 UV sequence, and then turn on the points. Now you can see we generate a 3x3 grid, and we can do this in our code. We first generate a surface, use the function rs add planar surface with with our polyline, and then we rebuild this surface with 3 inputs. The first one is our new surface, the second one is the degree 3x3, this is by default, and the last one is 4x4 points, the 4x4 UV counts. Then we store those new points. We store this new 16 points into a new point list called PTS. We can say use the function surface edit points with the input surface. Then we store all the points into this list, and let's take a look at the distribution of the list, I mean the index. Let's do rs4 I in range length points rs.add text dot with I as text and points at index I as position. Let's have a try. Now remove this. Just take this cell as example. We can use no, we don't need to make it so complicated. We already have this from polylines. We can remove this and call this function subdivide with just one test polyline. Front polys at index 0. Let's try it out. Yes, we have here. We have it here. The problem of this linear structure, I mean, the point list starts from 0 and ends up with the 15. This structure will cause us many problems when we manipulate our point sequence. Like if I select this point 13 as start point, and if we want to draw the square counterclockwise, there will be no point outside here that will cause an arrow. But if we select point here, there's no such arrow. So in this condition, we should set some conditional statement that we can't choose these points located on the edge. For sure, we can just manually type in the point index like 3, 7, 11, 15, but it's not computational. Maybe we can find a way to reframe this point structure to make it manageable and very easy to process. And my solution is put it into a dictionary according to its X index and Z index. So here, I declare a new point dictionary, which equals to an empty dictionary. Then I set X as 0. Loop over all the index of the point list for I in range length points. If I larger than 0 and I modulo by 4 equals to 0, then X plus 1. And the next step, I put the point into the dictionary according to its X and Z index. This is the Z index equals to, oh, there's something here. Okay, new point dictionary equals to this one. Then we can try to print out the text dot to see what the new structure looks like. I can do for key in new point dictionary rs dot add text dot. The text is the key and the position is the point coordinate at the index of key. Now that we can run this code, but before this I want to set the grid 2 by 2 by 2. I think that works. Okay, here it is. Let's run it. I should remove this layer of point dot. Run it again. Now this is our new structure. Now in this condition, we can just set a conditional statement that when selecting the point, we don't want the z value equals to 3, and we also don't want the x value to be 3. This is much simpler than the previous condition. Now we can just randomly pick point from these 9 points and draw the square counterclockwise. Instead of setting a conditional statement, I think a much more easier and more efficient way is we randomly pick the number from 0 to 2 in x direction and do the same thing in the z direction. So we need to import, we need to say from random import rand int, that is a randomly pick an integer that we provided in the range we provided. And let me see, I want to remove this code. Just down here, I want to say x star point as rand integer from 0 to 2 and z start value as random integer 0 to 2, and set the x step as random 1 to 2. This means x step is if the x step is 1, the next point is here, then we draw this circle, this square. If the step is 2, we have 2 steps in x axis, then we draw this rectangular. The same rule applies to the y step, integer 1 and 2. But in one condition we should be careful is if we pick this point, the x step shouldn't be 2, and if we pick this point, and this point, the y step shouldn't be 2. So we need to set conditional statement here. Says if x equals 2, the x step can only be 1. If z here, sorry, I messed up in the names. Z equals to 2, then z step should only be 1 as well. Now we go back to our old task, we pick points. PTA equals to new point dictionary x and y, x and z. Yes. Now we duplicate this code. Point B equals to x plus x step, z. Point C equals to x plus x step, z plus z step. The last point is z step. Oh, I should change this name. Then we draw a new polyline equals to rs dot add polyline. We are already very familiar with this kind of code. And ptd and pta at last. I think we have all we want. And let's run the code again. We have this one. But before finishing up this function, I still want to remove the surface we just generated. Like, I run this function again. There is a surface here. I don't want this surface. I can just delete this surface inside this function, which is, you use the RhinoScript syntax function as rs.delete object. Which object? The polyline as input polyline and the surface we generated. Let's test this again. Oh, it doesn't work. Let me see what's going on here. RS. Delete object polyline objects. It should be objects. We delete many objects. This must be work. Okay. We did it in a single unit. Then we apply this to all our units. Let's see the result. We increase the number in x direction and the z direction. Then we loop over all the squares in the front layer. in range length from polys. Then we call the function subdivide, and with an input front polys at index I. Let's try it out. Okay, we made it. Now we have the basic of our pattern. The next step is just to loft these two layers of curve, make it a solid object. Oh, I just realized I forgot to return the new polyline in this subdivide function. Add the last line of code in this function, return new polyline, and replace the old front polylines with the new smaller polylines, new smaller squares and rectangulars. Here is front polys, polys, polys I equals to the new polyline. We replace the polylines index by indexed. Let's test the code. Okay, it functions well. Now we are almost there. The last step is to make these curves, make these lines into the solid object. And this is more like a hard coding part. There's no a lot of tricky thoughts inside here, so this might be a much more relaxed part. Let's define the last function, solid, which takes two inputs, the front polyline and the back polyline. Oh, sorry, front polyline and back polyline. And we use the rs add loft surface function to generate the surface. This takes a list front polyline and back polyline. And we can run this code, run this function inside this loop. Solid back polys at index I and front polys as index I as well. Run it. The very last step is just to add the thickness to this pattern. So just follow up, guys. Oh, we have something to do. We need first offset these curves. We want to offset it with 0.1. We want to offset this curve inside, and we also want to offset this curve inside. Then we loft these two curves, we loft these two curves, we loft these two curves. Then we join all the surface into a solid object. Now we just need to offset the front polyline. I call it f poly_o equals to rs dot offset curve with the input front polyline and a direction which is the center of our input polyline. It's rs dot curve area centroid with the f polyline at index 0. We define the distance of the offset, and we also need to set the offset plane. Offset plane's normal, which is 0, 1, and 0. Copy this code. Offset the back polyline. Should be back here. Yes, that's it. This should be the first surface we generated. The second surface is rs dot add loft surface, the front polyline with the front polyline offset. Duplicate them 3 and 4. The front polyline offset and the back polyline offset, and see what we still need. Front polyline, oh yes, is back polyline and back polyline offset. The last step, we join all the surfaces. Use the function rs dot join surfaces. Surface 1, surface 2, surface 3, surface 4. All 4 surfaces here, and we hope to replace these original surfaces. We want to use the solid to replace the previous discrete surfaces. So we should set true at here. Let's see the magic. Yes, it functions well. Then we just slightly increase the number of our units in x and in z direction. 8 by 8. Maybe our last test today. And this is what we want on this RhinoPython and GhPython playground. Oh my gosh, my brain is running super slow now. And that's it for today's video. Thank you so much for watching. This is quite a long video, so I really appreciate you guys' patience. I already uploaded the code to my GitHub repository, and I put the link in the introduction part of this video. The next week's topic could be how to map this pattern to a curved surface like this. That depends on a completely different logic, and I might divide that video into 2 parts to make the contents digestible to everyone, to those persons who don't have enough time maybe. And welcome, come back if you are interested. If you have any thoughts, any comments, any critics, please comment below. I will really appreciate that. And thank you so much. Bye bye.